All right, I'm going to make this go away in a second here. I'd like to get started on today's lesson, but yeah. So, is anyone not confident they could fill in the gap there in the work? I mean, we could. Hopefully, you're feeling good about parametric equations and their applications. Lots of different things we can do. Lots of different things of different flavors in the homework last night. We got some Ferris wheel thing, and what else do we have? Some projectile motion stuff, baseball, lots of those kind of baseball. The baseball with the wind, do you like that? A little gust of wind, we'll add that to the x component of the velocity.
Was that like, do you have to do stuff from a couple homeworks back for that, or was that like a new thing?
Not necessarily, you just have to do, so the x component of the velocity is, instead of whatever it was, something cosine something, right? It is something cosine something plus 5. All that times c, right? I think it wasn't like 5 miles an hour.
16.03345308.
Let's talk about lines again. Is that okay? Let's talk about lines. Let's do it in let's talk about parametric equations again in 3 dimensions now, okay? So I think it makes sense. I think it makes sense for where to go with this, doesn't it? Parametric equations has let us take real numbers and have functions that map a real number to 2 real numbers, right? Isn't that what a parametric equation does? You give me one number, t, I give you both an x and a y value, right? So it makes sense that it would be very easy to have like a third function that gives you z, right? So parametric equations work great in higher dimensions too, don't they? Just add more components. So let's play with this idea with a very basic, with just a line. Okay, that's the goal today. It's just to play around in 3 dimensions with a simple scenario, which is just lines, just to get ourselves used to this. Recall this slide from the other day. I just copied and pasted it from that PowerPoint. Do you remember how to do the equation of a line in 2 dimensions? This is, again, copy-pasted from our previous PowerPoint. You remember? Position vector plus t, the parameter, times some direction vector, right? So that was how we kind of conceptualized the equation of a line. Well, the line in 3 space is the same equation, just with another component, right? So there's not too much to say. It's still position vector plus parameter times the direction vector, still. Now notice how easy that was to get an equation of a line in 3 dimensions. That's beautiful. In fact, I should have let you think about it first. Like, how would you extend your equation, I don't know, y equals mx plus b, and take that to the 3rd dimension? I think that would be a real challenge, as simple as lines might sound. But if you have it in parametric form, extending to the 3rd dimension is quite easy. Just add a 3rd component. Yeah. Sorry. The only new part should be this stuff down below here. So let's go ahead and try this. Go ahead and do this. So did you use A as the position vector? Zero minus 1 is -1. 2 minus -2 is 4. -5 minus -4 is -1. How are we doing? Great. And then how did you find the halfway point? Yeah, if you put t equals 1/2, that gives the point, what does that give? 1/2, comma, 0, comma, -4.5. Is that right? By the way, it also says to give the parametric equations. I mean, really, those are the same thing. But another way you could write this is like this, too. But you might be more comfortable writing it this way, too. Just remember, we've done this before. So what is x? What's our way of calculating x in terms of t? It's 1 minus t. Y is -2 plus 4t, and z is. So I don't know, someone might claim that they like to see it that way better. I don't know, whatever. They're the same information, obviously. So, remember, this is a very powerful technique. If you want to find the point 2/3 of the way from A to B, then let t equal 2/3. If you want to find the point that's like opposite, on the opposite side of A, than B is, right? But by the same distance, let t be -1, right? So there are lots of things. This is a very flexible idea of being at A and then adding some multiple of the vector from A to B, right? It's a very powerful idea. Yeah.
Does it make a difference which you use for the position vector?
It doesn't, no. So actually, we get the same line if we use this here instead. It's just, where would you be when t is 0? You'd be here instead. You'd be getting the same line, but you would be at different places than we are at different times, right? But over the course of your existence, you would hit all the same points in the plane as we in the space, along the same line that we do, you know? Good. Yeah, and it makes, by the way, any scalar multiple of this direction vector is appropriate too, right? Any vector that points in this direction would be fine as well, right? It just would be that you're going faster or slower along the line. So we have a lot of nice things to say about the geometry here. Does this correspond to the midpoint formula, by the way? I kind of like this way of thinking about finding the halfway point. Like if I give you 3 and 17, I find the halfway point between 3 and 17. How do you do that? Why does the average work, though? Does that actually make sense geometrically? That the average would be the halfway point? Why is that? Why? Why, though? Have you ever thought about like why the average is the halfway point? I don't actually think that's what you would do. What would you do if you had to construct the halfway point between those two things? You'd find you'd maybe take the length of that segment, which is 14, and then you'd divide by 2, and then you'd do what? Excuse me, what'd you say? You'd take 3, and you'd add 1/2 times the length of the segment? Isn't that what you would say? I just want to make sure you understand that, like I think we sometimes say that's the average, and I think algebraically you could prove that that is in fact what we just did. It's not the natural way to talk about the midpoint between 2 points, is it? Really, the midpoint between 2 points, if you're thinking geometrically, is more usually thought about this way, isn't it? Take 3 and add half of the distance. Okay, well here's the three-dimensional version of that problem, right? Like we're just doing the same thing. We're adding half the distance from A to B and adding that to A. So that's the same idea, right? All right, now we need to visualize this a little bit. Here we've got the 3D coordinate system, x, y, z. I'm looking for a line that goes to this point that's perpendicular to the xz plane. It's an interesting way to ask the question. So how do we find, what does that say? I mean, I don't know. Where do we even start? I'll take a suggestion if you have one. Or is there an equivalent way to phrase the problem that you like better? I don't know. Hopefully you can visualize this at least. You have some point. We want the line that's going through that point drop through this plane perpendicularly. Can you imagine? Another way to say that would be that we need the line to be like, I don't know, parallel to the Yeah, to the y-axis. Like we want it to come out of the xz plane the same way that the y-axis does, right? So we want it to be like just like the y-axis. It'll be maybe somewhere else, but we want it to be parallel to the y-axis. Okay. I still need to weigh in though. Yeah.
Oh, I have a question. When this is like containing 0, is that just like a point on the line?
Yeah, I should maybe set it that way. Maybe I don't know. Can you give me another point on the line? Oh, let's start there. Because we love having 2 points. If we have 2 points, then we can just do this like we did on the previous page. What's another point on this line? Cameron, go ahead. I'm going to disagree. What needs to stay fixed and what needs to change if we want to have this slide back and forth? I think that you don't have 2 degrees of freedom here. Franklin. X and Z need to be constant, but Y can change, right? Okay, so give me a point then. It's another point that's on this line. Unhelpful. Unhelpful. No, give me another point that's on this line.
0, 1, 3.
0, 1, 3, sure, right? All right, so one way to do this would be if you can even just geometrically think through this and get even one more point on the line, then you're good to go, right? Can't you then form the equation of the line? So I think some of you would be like, okay, that's great. X, Y, Z equals, where do you want to start? I don't know. We can use either one. -0, -2, 3 plus t times the direction vector, which is, what is the direction vector? 0, 3, 0. Not a coincidence that this is true. Is this very clear to you that this is a vector in the direction of the y-axis? Does its magnitude matter? Actually not, really, right? So actually another good way to write this equation would be like, you could just write anything that points in the z direction. Maybe you didn't have to come up with another point. Maybe you just say, in the y direction, excuse me, right? You could just say it that way. That works too. These are all the same line, I hope you realize. Would you like to use a different point here? That'd be fine. You want to use like 0, 0, 3? You could use that as the position vector. All of those describe the same line, don't they? We're at different places at different times on the line, but they all describe the same line. In fact, if you use parametric equations to write it down, so here's a great way to write it. If you write using parametric equations, don't we really just mean the line where x is 0, z is 3, and y is anything you like? How do we say that? Right? There's a good equation for the line, right? I just want you to have you free your mind here a little bit. Yes? Okay. X and z do not change.
Yeah, why do they not?
So if you have a line coming out of the xz plane, then we want the x and z coordinates to stay fixed. And what is it that changes as you slide out away from that axis? Only the y coordinate, right? Yeah. Quickly explain why these lines are parallel. Even though you've never seen them before, and they look, well, tough. Ew, they're terrible. Yeah, the only thing we care about here is the direction vectors, right? So if the direction vectors, we just had this discussion on the last slide, you know that these are parameterizations, that point in the same direction, right? Does this feel familiar, by the way? I know it's a weird context, but like you did think about this back in Algebra 1. When are lines parallel in Algebra 1? So this is kind of saying that their slopes are the same, right? We're having fun here. Okay. We're blowing your mind. That's not going to work. All right? Let me show you one more thing before you go, please, if you'll allow it. First of all, are these even lines? Oh yeah, I guess they are. They're written in a terrible way you probably don't like. But they are lines. We have x, y, z equals some thing for x, y, and z here. Okay, so do these lines intersect? And by intersect, we're going to mean at some t or s value, right? Or some at anywhere, we don't care if it's at the same moment in time, right? We just want to know, do they have the same? Is there a point x, y, z that lies simultaneously on both lines? So I might write this out. Here's the first line: x equals t minus 8, y equals 2t minus 6. I probably should have just given it to you this way. That would have been a nice thing to do, right? And the other line is x equals 2s minus 1. I'm going to change it to an s if that's okay. And z equals 3s plus 5. The reason I'm using a t for this line and an s for this line is to emphasize with you that it doesn't actually matter that the t be the same for both lines, right? So just to emphasize this, I want to change the parameter of the second line. We don't need them to have the same parameter at the same moment, right? Where they hit that point, t might be 7 and s might be negative 43 or something. That's okay as long as they go through the same point at the same time. So do you see a way in how we could maybe come up, see whether we ever get the same? Right? Are these ever equal, is the question? Let's suppose they are and move forward, right? If they're equal, that would mean that t minus 8 is the same thing as 2s minus 1, right? Isn't the x coordinate would agree for some proper choice of t and s, right, on the two lines. It also means that 2t minus 6 would equal s plus 2 at the same moment when you pick that same t and s, right? So can you find the t and s value that satisfy simultaneously these two equations? So solve for t and s. Like I said, I'm kind of rushing at the end here a little bit. I apologize. And then what about the last equation? We didn't use it? Well, I do still want you to use it because what should still be true? This is kind of an overdetermined system, like there's too many constraints. But it should be true that whatever t and s you do find should, what do you need? You still need to check if you find t and s. They should work in the two equations to make these equal. But what else should be true then? If you plug your t and s you find down into here, it should work with the last one too. If not, then that's a problem, right? Then they don't intersect. It's very easy for two lines in 3 dimensions not to intersect. The homework tonight is this worksheet. Oh, there's no book homework. There's no book homework. Just this worksheet. Have a great day, guys.